So, good morning, everyone. And I would be taking the vehicle basics of vehicle dynamics. Just a minute, I will open my video also. So, a lot of things has been talked about, and one of the thing which everyone is correct in the vehicle dynamics and vehicle handling, and you have heard the various aspect of vehicle dynamics and different views point on the dynamics per se, and spending almost 20 years in this field, and I have come across various instances where I started thinking that there is nothing wrong in so whichever way you put it, there will be always an alternate way to prove you wrong. Okay, so normally I use this term, there is nothing right or wrong in vehicle dynamics area. Everybody is right in their own perception and in their own development philosophy, and which put up a challenge on people who really wants to understand that, okay, is it something written in a black and white or one particular direction, that this particular thing is right, and if I read this particular book, I will become an expert in vehicle dynamics. And this is one thing which led many people getting into dilemma. How do we come across this situation where we were able to take the right call? And vehicle dynamics is or vehicle development per se, or the right vehicle control set. It is more or less the choices. What kind of choice you will make for a person who will take your vehicle, or who is going to put their money, or who is going to take the vehicle for a different purpose, whether it is to do it for their profession, or to for a luxury ride or anything. And this brings that it got a multiplicity of meaning, which Anand also covered in his presentation, and it applied to most of the people say, okay, it's steering, right, and handling. How do people feel it on the public road? Whether the car is good on some rough road, whether I will be safe on high speed stability. Do I have a control on the car? So if I do a cornering, will I be able to control it? Some people also say it, okay, how do I feel in terms of noise, vibration, harshness? Is the car is quiet? And some people also say it's related to aerodynamic. And that is where we, at Tata Motors, we said, okay, it's a dynamic property defined by the occupant perception. We don't put a name tag on, okay, this is what vehicle dynamics is. We said, okay, this is the occupant perception, and what he wants to do in that car. How do we can put up him as a on the stage and give him what he wants, whether in his terminology, vehicle comfort, in terms of what is the quality, or eminent, what he perceives as a vehicle dynamic. We would like to deliver his interpretation of the dynamics. We don't want to put down that, okay, Tata Meter or we as a dynamics engineer, our interpretation of dynamics is this one, and that's what you have to live with it. It's the person who is owning the car, or who is the occupant. It is his perception which makes dynamics. Now, there are two important things which a lot of people talked in the morning, and I would cover it up. It's a wide range. Okay, so basically, if you consider the vehicle characteristics, they vary from the type of the suspension in terms of, let's say, a truck or car, or different kind of suspension in the car category also. Different track, tires. We have heard Mr. Isaac is talking about a lot of things on tires, and which is a critical part into the delivering the vehicle characteristic. Wheelbase, if the truck will be, which will be having a very big wheelbase on the car, which is shorter or smaller further. Then comes to the lower number, that how do you feel the center of gravity, the weight. Now, weight we have slightly put at a more wide, bigger font. It's the weight is critical parameter to define characteristics, like a truck to a car to a EV. So all these weight becomes one critical parameter which govern a lot of vehicle characteristics. And then comes the tertiary parameters. How do you set up the roll stiffness, kinematics compliance, steering system? So all these things and many more, these define the vehicle characteristics. Finally, we have, as a vehicle dynamics engineer, we have to define what do we mean that a vehicle characteristic should be. And to put down into words, we said that the vehicle characteristic should be when we say it is a good vehicle, or we say it's a big vehicle response, we all need a vehicle which is stable. We tends to want a vehicle which is predictable in all possible environment. We need a controllable. It should gain and delay suitably to the human drivers. It should be able to, you should be able to predict and control the vehicle. And it should be linear. It should not give you surprises. And we thought that putting into characteristics into a more textual form will make us what do we really need, and irrespective of track, weight, or the different kind of suspension, this is what a characteristics of the vehicle should be, and which we as a vehicle dynamics engineer would prefer to do it. Now, the second part of the story comes driver characteristics. We realize that many times we say, okay, there are a good driver and there are the drivers which are not so good. Okay. But we said that no, each and every driver is having certain characteristics to their role, to their job profile, or to their expectation. And one particular driver can also play a different role with the same car. And these pictures, which we took it up from the internet, describe the variety of driver characteristics. And if you go, somebody is doing a high speed, somebody is just doing for their own regular purpose, or taxi driver, or a lady driver who is learning, or somebody is confident, somebody using the car as a for a family trip. They demonstrate that what kind of variety of driver characteristics we have. And as a dynamics engineer, we need to live with these kind of characteristics before we take a decision on behalf of them. And that's make a big responsibility on each and every dynamics engineer, because we cannot take a say that we did not thought of this kind of maneuvers, and that is the onus on us. And to define these again on the words, we said that there can be driver characteristic which can be sophisticated, who have a good capacity and great capacity. We call them expert. They are expert because they have good control. At the same, sorry, at the same time, they can process a lot of information and assess or control the execution. And then the term comes lazy. These are the drivers which rule wide minimum effort, and they really feel that okay, I should be put up minimum effort, and if required, they adapt to a new situation. So where the sophisticated driver, if he, because he is processing lot of information, and if suddenly something comes, he will be able to adapt to this situation faster than a lazy driver. And we need a better control on a stable system. We need lazy linear responses and small delay to moderate gain, which are the requirement for the driver characteristics. Now, as a dynamics engineer, our response is to make vehicle properties which should adapt to the general driver characteristics. if we start designing car for a sophisticated, we may not be able to fulfill the dream of the people who don't want to take those many effort, or they don't want to process these many information which are available to them. Or if you design a car for people who have minimum effort, the sophisticated driver will feel that car is so restrictive that I am not able to enjoy it. And this is where we have to decide that these two characteristics of vehicle characteristics and driver characteristics should match. Okay. Now, how do we match it? Then this is very common term that okay, we should match, and how to do it. The how part is more dangerous because it need to be thought how the process should driven. How do you do it? These how do you take that vast information coming from the experts in terms of suspension architecture, weights, CG, and second, there are multiple vehicle opinions maker in terms of drivers. And this is where we say, and long way we studied this, there's a open loop and closed loop system, where open loop is where you remove the driver part of it, and you do all these analysis in terms of CA, in terms of objective handling, and it becomes an open loop system. And when you add subjectivity, this becomes a closed loop system. And this is what we followed for many years in terms of driving dynamics development, that there is a open loop and closed loop system. This is a slide which Anand also have covered, that the open loop and subject closed loop differentiate differently in terms of where objective evaluation brings the numbers. It brings the reality. It talks about the matrices and statistics. It can be created mathematical models. You can have a general situation like a steady state handling test. So if you run 10 times a steady state test at a different let's say different day time or different days on the month, you still get the similar number. That is a fact. But subjective evaluation does not work like that. Subjective evaluation is like interpreted repeated reality. And many times you may have realized the same car, if you drive it in a two different days, you find it slightly different in the perception, because what you felt at that point of time, many times we feel that okay, the how much you have eaten on that particular day or what was your mood can also have a certain interpreted reality differently. And it depends on the opinion, and like experts opinion, people does it because of their past experience, because of their strong opinion that okay, I would like to have this particular car in this particular fashion. And they would sometimes get bias, sometimes they have right opinion, and but the results can vary. Okay. In terms of stories, that if somebody have taken the car and he got into some incidents, he would like to tell you, share the incidents on that particular maneuvers. And there's no proof for that particular because you don't know the environment, you don't know the what situation, what kind of input has happened, but the feedback is right. So all these things create a disconnect between objective and subjective evaluation. And like we said, we have to decide or take both in the right perspective to find a solution. Now, in terms of customer expectation, if you see that there is a band of family car, sports car, safety, comfort, and excitement, we have put up in 4. In terms of family car or sports car, we earlier around 20 years back, we had a lot of difference between family car and sports car because of different enthusiasts and other things. But this is getting widened up. in terms of more and more family cars are becoming more safer. They can be driven at a much higher speed. So at the same time, sports cars are become more and more comfortable. And this is the requirement that customers or the people wants both side of the excitement and expanding these boundaries. Now, in terms of safety and comfort and excitement, the boundary itself is moving outward. And this is where we come in a situation that once the overall sports car and family cars are having more closer dissociation, the overall boundary in terms of comfort and excitement and safety is changing. Now there are system like vehicle characteristics more safer. Okay. Hello, am I audible? Dipanshu? Yeah.
Yeah, you're audible.
Yes, yes.
So, yeah. So there is two ways to do it. One, to make the system like vehicle characteristics more and more advanced. So there we come as a part of getting a better tire, getting more advanced technologies on suspension architecture, and bringing it more and more linear or responsive car by doing the weight balance, choosing the right hard points, making more advanced suspension time. The second part comes is making the driver more advanced. And this is where we are in the era where ADAS comes, and what it is doing. A customer who is, let's say there are two, one is sophisticated and one is lazy in our term. The ADAS will make the lazy customer to more advanced. Okay, it takes the call which a sophisticated customer would have taken, and what we are doing to convert a lazy customer to more sophisticated, which means that everything comes around into this situation where you can make the vehicle characteristic more better, or you make the driver more responsive. Now there is a two part of the ADAS is pushing the other part, which is the same way, the same situation where we are trying to make the driver characteristics more predictive. Now the question is again, the person who is doing the ADAS tuning is taking a call on behalf of the driver characteristic, and that brings more responsibility on the people who does the vehicle dynamics development to make those right calls. So in terms of dynamics engineer, their headache or their challenges will not come down. In fact, we will have more and more bigger challenges in future. And to summarize this particular story, customer expect a vehicle to be refined and durable and meet a legislative standard. The second part is if the customer is to distinguish between vehicle other than styling and brand, OEM resort to vehicle dynamics to characterize the vehicle image that is to be portrayed. Now, OEMs have their own way to do this. And when I say how we should differentiate, if you see the people in a particular organization will bring their DNA, and they decide what should we do as a vehicle delivery, our perception of drivers and our perception about a vehicle. And that is where each company will have their own DNA kind of structure where you can identify it. So if you sit on particular car and close your eyes, you will be able to predict, okay, this is the car I am sitting. That has come from years of their development work and their philosophy. Now, in terms of everybody have to go through the same basics of vehicle dynamics. It got the three part. One is the lateral dynamics, ride comfort and braking and acceleration, and the yaw, which is lateral dynamics. We, in a theoretical word or in a more development work, we say, okay, our interested for dynamics per se or dynamic control, it's a frequency between 0 to 4 hertz, which are more important for us. And this slide, which we have common, is how the vehicle dynamics define into some terms of isolation and control. And we have divided that what contribute to isolation and what contribute to control in terms of path, in terms of speed. And if you change, whether you change the path or whether you change the speed, the characteristics of vehicle will change. The parameter which is more important to us is stability, agility, fidelity, and linearity, which comes through our earlier understanding about vehicle characteristics. So we need to bring it more linear response of the vehicle, more agile and more stable. So those are the parameters which still govern and bind us into these particular parameters and put out into a more numbers into this. Now the second part comes challenging. How do you do this balancing act? Because like I said in the start, it's the choices. It's a choice which a dynamics engineer have to take, that what do I need to do in terms of isolation, which one is better. And like I said, there's nothing right or wrong in vehicle dynamics. Because it is all depend on what kind of market, what kind of customer you are looking, and which is the more customer and which you are focusing, and without affecting the masses, can you deliver this balance? And the better balance which you will be able to do it, people more and more driver characteristic, the wide range of the characteristics of driver, if they are able to appreciate it, then the vehicle dynamics engineer will be more happy that, okay, I took the right call. And where I have texted it like control means sporty, stable, fun to drive, good cornering capacity. Isolation is comfortable, quiet, and easy to drive on the rough patches, etc. For that, these kind of people, the comfort takes supersede of the good cornering capacity. But in the right balance need to be done. And the second thing is, how do we do it? And this is where we develop certain things along working with various our own UK partners and all these people, that every time you need to have this decision how the attribute need to be balanced. So for example, people talked about that ride and handling is opposite characteristics. If you try to push too much of ride oriented, the handling may get compromised. Or if you want to make a very sporty car, you may end up poor handling until the system or the technology is supported. So there is two part of it. If your customer is ready to pay for the technology, you may be able to pull that boundaries itself outward. Okay, so you can use the advanced system like air suspension, magnetized suspension, all those things. So you push that boundary outward. But if you have to live in this band where the customer expectation is within this, you have to decide where do you want to position your car. And how do you position your car depends on your ability to assess this with the objective and subjective result. There can be different brand positioning which you have to put up and then say, okay, this is what our position will be. And if you want to change your position, you need to take action. So for example, if brand A want to move upward in handling, they have to decide that how do we do it. So there will be hard point change, there can be change on the stiffness, there can be the parameter like seat itself you need to change. All those things you have to decide. Similarly, in terms of steering, in terms of corner controllability and this effort, the response from steering field when you do it on the high speed stability and other parameter and the effort, many times you find that, okay, which one is the right, whether we need to put up a more torque feedback, or which do I need to put a less torque feedback. How do we perceive at high speed effort in terms of vehicle? This is a call which vehicle dynamics engineer need to take, that, okay, where do we position our car? Okay, now this is where we say, okay, this is the DNA, because the vehicle dynamics engineer could have taken this A point over here also. He could have put that car over here also. This is the choices of the company, and this is the market. How do you recognize? In a development world, we put it into this very nicely placed with some of our consultant also, that how at a user level people need a sporty and fun to drive. In an expert level, people talk about linear, neutral, progressive, balanced car. In terms of objective engineer per se, they will talk about roll, understeer, gradient, more numbers to this. And in terms of design engineer per se, he will talk about roll steer, stiffness, in terms of wheel rate, in terms of compliances. So at a different level, and these people can be 4, these people can be 1, these can be 40, and but their language will be in the similar term. And as a vehicle dynamics engineer, you need to understand the mindset of where they are coming, and use all these information to decide something which we say target. And target will be defined in terms of where do we want, how the vehicle characteristics and the driver characteristics need, and to come out with a goal that this is where we would need to go. In terms of just to explain this in a more handling per se, this is a vehicle which is doing a cornering. Now, in terms of technical, all the technical word, we are saying, okay, the car is having certain roll axis, certain yaw, the car is also going to have a yaw and certain pitch because of weight transfer. And there is a lateral force coming on the tires, which is making the car to slip, or the slip angle is getting generated. Now, if you try to put all the information which I have said, it will have a certain aerodynamics drag. It will have the weight transfer happening. It will have certain pressures coming onto it. Now, the kinematics and compliance of vehicle geometry per se, what kind of caster, camber, toys you are having, what kind of suspension system you got, what kind of dampers you have, and engine powertrain, how the torque is delivering, what is the track of the car, how the roll axis has been set up, and what is the rear suspension. Then you end up into one critical item which we all accepted, the tire being a non-linear component in that grip performance. It plays its own role, what kind of surface, whether it is a wet, dry, what kind of road interaction it got. And this also plays a critical role in that particular maneuvers which you have ended up. Then it comes, who is the driver? And will he be able to push, or which will he or she will be able to control the car on that particular maneuver? And the one additional thing which we cover, that with the environment. So I took this picture on Indian road, that somebody is pulling a horse through his scooter, and this many terms you won't be able to predict it. Okay, so these are the condition which you are not knowing. And if you see now the screen, it's quite a busy one. Okay, and this is the challenge which we all face, that we look the entire dynamics or vehicle dynamics in this particular window where everything is happening together. And this is where we have to work, and this is all the situation, all the maneuvers, all the parameters working all in sync. I have not added the electronics part of it for the simplicity, but if you start adding the electronics part, the how the ESP is going to kick in, how the other part of EPAS and all those things is coming in, it further become more busier slide. And this is where we are when we start a program, that okay, all we need to define. So how do we make it more simpler? We go with the basics, that just make it simple, divide this entire thing into small windows, that how do you control the each and every aspect of this. So let's say weight distribution. What is the preferable weight distribution? Do we need to, if it is a front axle weight is more than rear axle weight, or it is equal weight distribution, or the rear heavy weight. Accordingly, you decide that okay, if the all the tires are having the same size, it's a simple that okay, if the weight of the front axle more and the tire size of the front and rear is axle is same, the front axle will have more slip angle generated and the car will have more for more understeer characteristic. If the rear weight is more and you have the same size of the tire, the rear tire will generate more slip angle and you may have a car which is oversteer. Now, once you have understood that, okay, the weight distribution can give you a different understeer level, this problem can be solved by multiple way. One, you can select different tire sizes itself. We did it some of our program. Second, you may ask the electronics to control. So on a corner, you don't allow the weight transfer to happen. So before the car starts skidding, you put it into braking. And that is one more way of solving it. Third, you can make the different tire characteristics itself, or the situation. So once you know the problem, you will be able to find a different solution to this particular issue, that what should I do? And these are the challenge which keep on coming. If you got given a car which is having let's say front axle weight is less than rear axle weight, and if you try to find a solution like okay, I want to just try to move the rear axle weight to front, that solution might not exist because you have a limitation of the architecture. So identifying a problem and then trying to find the right solution in that particular segment is the key for the vehicle dynamics engineer to decide the way forward. Same thing like in terms of suspension kinematics effect, we have seen that okay, well, this is you will find it many theoretical or there are good books and available in the market. You will find okay, there is a mathematical model for all this. So in terms of vertical motion parameter which we are more interested is bump steer, camber angle change, wheel track, and the roll center height and wheelbase. So these are the vertical when the suspension move in vertical direction, how this particular thing will work. So the machine does it or the CAE does it to move the wheels in different vertical motion. The desirable attribute we put it that okay, we want to keep body frequency in particular range. The wheel of frequency should not generate additional asymmetry or in terms of or any abnormality. We need a progressive bump travel because if you make it non-progressive, the your requirement of linearity will take a call. So third is large wheel travel. We need to give as much as time for suspension to travel in that range so that you have more option to play around. So if the suspension travel reduces, you have everything running very fast. So a bump stopper come in contact very early, and then the forces generate very high, and then you have to have a reaction time further low. So all these have their positive and negative. The large wheel travel will also create a problem on a shorter car because you may not have space to accommodate that kind of big travel. And this is where the dynamics engineer to decide how do we, what will be the right level of travel for that particular segment where we will be able to tackle all kind of situation. So these are the challenges which comes for all the manufacturer and the segment which we are in. In terms of roll motion, so the same vehicle when it goes to roll motion is we talk about one wheel input. The one particular wheel goes in input and it gives all the enroll bar and the roll stiffness play, and also the how the roll center has been placed. So have you set up your car at a very low roll center at the front and very high at the rear, or you have made it opposite? How do you place your roll center height, which have its own effect on the weight transfer, and which create a parameter which we should be able to understand and see that what will be the right for us. all these parameter, when we decide, we do evaluate with the different CAE capabilities, where we model it and decide the hard point position, that what should be our front suspension hard point, what should be our rear suspension hard point, how do we put a bush which are there in the system, do we need to have a non-linear bush or particular directional bush, all those things we do it on the, and with the help of multi MBD team, and come back with the solution. Now, one critical aspect on further to it, these are the part which I have said post everything is set up. We set up the hard point, we have set up the weight transfer, we have set up the roll center height. Still, we have certain level of uncertainty or the liking, where we can fine tune the car basis various application. So we keep certain tunable component. So in terms of spring, we can play around the ERV. We do a lot of work in terms of damper tuning. So how the damper hydraulic should behave. We spend a lot of time to fine tune dampers, which gives us the right level of characteristics which we need. Then bush also, in terms of, if we find that okay, particular compliances we are not happy, or the tolerances which together of tire and the spring and the hard point, they will be more better if we change the bush stiffness in a particular way. We do keep it as a tunable option during our subjective assessment. And the bump stopper, how the bump stopper linearity or the non-linear curve should be. The reason for this keeping these tunable parts is very simple. One, there is if we do it all, everything would have been in a steady state. We would have never needed this tunable part, because everything is steady state and predictable. But after certain speed, let's say if you are driving at 80 kmph and if you are doing cornering, many non-linear behavior patient, like the rubber tire characteristics at these rubber compound, then the rubber used in the bushing, the structure itself will have certain higher load which can have a deflection effect, which you may not have predicted. And the overall setup of the hard point and the non-linearity range. So to compensate that, we do keep it a certain tunable parameter, which help us to go through a certain thing which may not be predictable in the steady state. Although the challenge for all of us is to have more and more predictability software in the CA domain, which all the OEMs or the suppliers are working in the similar range. So once the vehicle is made, where you have got a tire which you wanted to like, you have suspension has been set up, you have put down all the maneuver, all the evaluation in the simulation domain, and it's meeting all your problems. We do end up into creating a prototype and building those mules and evolution vehicle. Now, this brings to me where your vehicles is available. It's very much there. You can get into the car, you can drive the car, and you can feel the vehicle. Now, it is like, okay, you got a competitor car and you have your own car, and you want to, how do you compare these two things? Our way to do it, we put these vehicle into, first thing is whether the car which we have built up is meeting our expectation. And so we do a lot of K&C work, making sure that whatever we drive should be true to our whatever we intended, and making sure that if the intent is right, then only we end up driving those cars. Because if the car is not set up to what we have intended, then the subjective feedback or the objective result may not be true to the expectation which we have. Hence, knowing the car before we end up doing objective or subjective, whether this is what we designed for, is very much important to us, and which is where we made a change in 2004, where we installed this facility, which is SPMM, which makes sure that before we end up getting into a vehicle, we know what we are driving. Then once we know, get into the vehicle, most of the thing which we always thought that ratings would capture everything. Okay, so we give it to 5 or 6 people and they rate it to 1, 2, 3, 4, 5 different scale, and for the ride comfort or the for handling. During evaluation, we realized that rating is not the only way people will be able to put their expectation. The people will be able to put their expectation when you ask them questions and ask them what really they felt. And a lot of debate happened to what, rather than asking them, okay, what do you like or not, we started putting those words that, okay, do you like the car in terms of ride? What do you feel that, where do you feel that perception? How do you find that steering, whether it was good, how perception, or do you feel any issues? Because if I put in a rating chart, the people will only put, okay, I have a static certain parameter, I have to rate only on this. They will not put their opinion into the paper. And sometimes we also put, if the diversity is not included, we do put down as a concern that, okay, if somebody says, okay, it's if it is the steering is too light, we do go put up a check whether this is light for a particular driver characteristics, or we need to check it from more diverse audio or drivers, which will give the right balance. So, for example, the steering light for a male might not be as required characteristics for the female. And these kind of diversity we have to build into our system from the day one, that how do we, the entire audience or entire driver people or drivers notice this car, and they all are the user of that car. You cannot make it too biased to one particular audience. And same thing for the brakes. And if we find there is a divided opinion, we do go and recheck it, that what is right. We don't, so it does not mean that ratings are wrong. It does not mean that people are not expert. It is a divided opinion which we need to verify it and try to put into more words what exactly is happening. And then we take help of our objective measurement also, what is the reality. And lot of debates happen in this particular. In fact, we have a very vocal people. You must have heard Anand also putting up his views, and all these views in very open and we have a lot of discussion around it before we make a choice with what is right. In terms of vehicle cornering, per se, let's say certain thing which is all of us know, that speed, when you are entering into corner, what speed you are getting into, what steering input, if are you going on a green line or are you getting into red lines, how much steering input you would need, what is the tire grip, are your tires having sufficient grips, what kind of road conditions. Some of the top morning discussion, that when you are going on a corner, you have some grit or some loose material, and if it is a wet road, it changes the parameter. Now, who should predict it is the driver, who should be driving, who should read all these requirement and make the right call. And which is where I said, if the driver does not take the right call, the electronics or the system is, we are forcing that to take that particular car. But if drivers take the green car, he's particular definitely in the safe hands. Now, in terms of kinematics compliant and load transfer is happening because the curve, what speed you are going and how sharp the curve is, define the load transfer happening in that particular car. When we talk about kinematics and compliance, so at the same time it is happening, what is the roll steer you have put up, how is the roll stiffness of the car, how much is the camber change is happening. So if let's say if a car is having a good camber change, the contact patch of the tire will accordingly have more contact patch at the surface, and which will provide you a good grip. And if you have a poor camber change at that particular corner, even a good tire may not be able to perform better. So it depends on how the camber change on that particular car has been set up. Then what a kind of roll center height which governs the load transfer of that particular vehicle, and the weight distribution. So if your vehicle is indeed front heavy, that you may end up into understeer, which you have to accommodate during your steering input. So all these things work hand in hand in terms of defining the target, all at the same time understanding the target for that particular thing. And this further goes to rate of steering input. The rate of steering input I purposely put up over here, that if you are entering on the particular corner, and if you are prepared for it, so you anticipate almost 50 meter ahead that there is a corner coming, there is a road sign board, and you were able to predict that there is a corner coming ahead, then you prepare yourself to enter into the corner. But somebody who missed that particular signboard, then suddenly the road corner comes in front of him, and he start turning the car very, very sharply. And the change, the way the steering input has put into the vehicle will also change the how much yaw gain happened, how much is the delay, how the vehicle responds, and accordingly you have to react. And most of the problem happens that if you delay that particular incident, then the car may go into maneuvers which need a more heavy correction or the counter action. We say counter steering. And many people may not be trained to do that. And that is where the theory comes that, okay, before we enter into put the customer into this particular situation, can we add into more electronics into it? And that is where the ESP comes in, that it detects it much earlier with the yaw, how much is gain, and accordingly break it. If ESP would have not been there, at that same time the vehicle is asking you to do a counter steer so that you control your path, and also you need to reduce your speed so that you reduce the load transfer happening in the car. Doing these two things together in a short duration of reaction time of any human being becomes a more challenging situation. Hence, these are the electronics intervention which help to detect it correctly and help the driver to become more safer. Now, this is the basics. How do you control? Where do the ESP should pick it up? How the intervention should be done? Where the intervention should not be done? If you detect that, okay, the customer is able to do it correctly, you don't want ESP to unnecessarily intervene it too heavily for the people who know how to drive. So these are the challenges which people, the dynamics engineer take, and these are the part of the tuning cycle. Now, in terms of when I say that whenever we have a doubt on the subjectivity, we do go back into the objective measurement, and these are the tests which is widely recognized by all the experts, supplier, and people who knows the anyway. Steady state circular test, lane change stability, Sine test, and frequency response tests are widely accepted. The steady state test gives you more control maneuvers. You will be able to remain in steady state maneuvers where the non-linearity of the vehicle does not picks up, and you will be able to do more design work in these or simulation work in these. In terms of lane change stability and Sine test, it is more like where the non-linearity of the tire or the other hardware picks in, and you need to have more better way to understand these maneuvers and analyze those data in that perspective. So you will still get consistent number, but you need to be having a more better way to assess it into that. The frequency response test is one particular thing where you have certain input, let's say steering input, and you check what kind of response parameter which we do it. The higher the response is also not good, the lower the response is also not good. So it depends on the characteristic of the vehicle which we will be looking, and accordingly this entire thing will be set up that okay, this is the right level which we as a OEM would like to be more happy to put up our car. Typical parameter which I have, and I'm sure that the next session will give you in more detail about how do they do it, what are the challenges of this. Typical output where the instrumentation I have put down on this slide that okay, we look into the roll gradient, we look understeer and oversteer tendency and the limit slip angles also. In terms of Sine dual test, we for the repeatability, we do use the steering robo and make sure that all the data is analyzed, and how we analyze this particular information, put it into our checkpoint, and take a goal for this particular thing. Now, to summarize the challenges from us, yes, in terms of handling, we, like I said, vehicle need to be controllable and safe for almost the drivers who may not be have entered into the difficult situation. So this is one challenge which we are trying to cover it up with the more electronics and ADAS is getting into picture. And the second challenge is we need to, as a dynamics engineer, we need to make sure that we should meet the version of vehicle dynamics like the customer wants. We don't need to put what we feel that this is the dynamics which will be, because customers sometimes they are right, and they are exactly know what they are talking. It is the diversity and the different characteristics which we should be able to meet, and this is where we feel that this is going to be a challenge, whether it is ADAS or ESP or any electronics, because the decision maker will be still some of the us making that call from our perspective, and we have to make our customers views very, very strongly in the tuning or in the electronics, so that they does not find difficulty to adjust to those situations. So that's all from my side. If you have any question, Dipanshu, and I try to cover it up considering a lot of things has been talked in the morning in the similar aspect.
Thank you so much, Mr. Vivek. There are a few questions for you, and in the interest of time, I would just take two of them. The first question to you is, how do you balance system response feedback to driver between comfort and sporty types of customers? What is the strategy being followed? The question is from Mohan Shanmugam.
So comfort and let's say handling, they depends on what kind of customer segment which we are looking. So if it is a particular comfort which we feel that okay, this segment need a more comfort, like a sedan which need a more comfortable car over a hatchback which will be more sportier, we would like to put that particular situation that okay, this comfort will be taking a more priority, and set up a system will be more softer, use the bushing or the tire pressure or the tire profile itself in such a way that all together works in the same direction. If we decide that okay, this particular car will need more sportier, then all decision will follow in the same way. The suspension will be more stiffer in terms of tire profile, maybe more lower aspect ratio, and the system will have a different kind of damper tune, all the rubber characteristics which we have.
Okay. Second question is from Mr. Ajay Sankran. He wants to ask, how tire size have effects on weight distribution?
So tire size, let's say there are different way to look at it. Tire size can be in the track or the tire profile, let's say 2.5, 65, R15 or R16 in terms of diameter, in terms of the cushion height, or in terms of the contact patch. So if weight transfer in terms of if you have a very low grip tire sitting at the rear end of the car will start skidding before any weight transfer start happening. So the slip angle generated at the rear will be too low that you may end up into skidding the car before you actually started the load transfer. Now, if you put a very heavy grip tire at the front and rear, the grip will overtake everything before the load transfer. So on a corner, you may end up, you need to drive at 100 km before you start heading to actual load transfer, which change the slip angle. So it's a parameter which need to be looked in from the all aspect, whether we are talking about grip or the size per se. But yes, you can play around to have the right balance.
Okay. Thank you so much, Mr. Vivek, for joining us today. Now, I would like to invite Mr. Andreas Pfister to give the presentation. Mr. Andreas Pfister is an engineer with Pfister Driving Dynamics, Germany, which is into driving dynamics and measurement techniques. He is the project manager for data acquisition and data evaluation systems.
Hello, everybody, and a warm welcome. And thanks for being invited to the Motion in Control. For me, it's a great honor to be part of this conference. This is Andreas Pfister, and in my presentation, I will give you an overview on some test maneuvers in vehicle dynamics. And I will start with telling you about my first and very impressive driving maneuver I had. That is driving in a steep curve. You see here the line, the yellow line. And when you drive like here the marked car, you are really in a vertical position. And when you drive fast enough, that's really impressive. Yeah, that was a very long time ago. And here the pictures are not so some years ago, but yeah, when I did this the first time, that was in the 1980s. Yes, and I learned very fast that that's not really driving dynamic maneuvers, because you're only driving straight, and that's not a normal position or driving condition or driving outside on streets. Yes, I'm engineer in vehicle and driving dynamics and measurement technique. I often say driving dynamics, yeah, when I think about driving on a test track, making maneuvers, and vehicle dynamics is for me the big thing behind this, with theory, with simulation, and so on. So let's say driving dynamics for me, I make a definition that's more the part here of measurement technique and driving the tests and make evaluation and so on. And yes, now I'm more than 30 years in the company Mercedes-Benz, and I worked there in the research and development for driving dynamics. And now I'm here as a private activity, PDD, that's Pfister Driving Dynamics. That's outside of Mercedes-Benz. It's my private activity, and I asked the company, and they agreed I can do this sometimes a year to make some lectures or to give some presentations. And in my work, I have a lot of activities in driving dynamics, the sensor and measurement technique, the data acquisition and also evaluation technique, and data knowledge management also. So that's all of the areas in driving dynamics. So for me, driving dynamics is a part of vehicle dynamics. And you have here the measurement devices, the sensor, also the software that's needed in driving dynamics, and the installation then in the car for the measurement technique, and then afterwards making the driving the maneuvers, making the tests, and finally the data evaluation, the analysis, and calculate the characteristic values you need. So it's a lot of cubes, and the job is to bring all these cubes together. And for today, we will discuss a little bit what maneuvers are important in vehicle dynamics and what do we need to measure and why. Then we will have a look to the very famous and common test, steady state log test, the lane change slalom test, and finally the sine versus dwell test. So here I have an overview, important maneuvers in driving dynamics. And on the left side here I have some groups, the standard maneuvers on high friction, standard maneuvers on low friction, extreme tests or steering maneuvers, and finally here some special maneuvers. And when we have a look here to the standard maneuvers on high friction, you see here a lot of maneuvers, a steady state circular test, the step steer input test, the yaw velocity gain, sinusoidal steer input, lane change and slalom tests, accelerate and braking tests, power off reaction, rev up reaction, braking in turn, the lateral wind generator when you're passing the lateral generator. And you see mostly here are very famous and have standards, international standards, so you can read in the standards what are the driving conditions and what is the evaluation tests and basics. But every company has its own special setups and to do a lot of additional things for characteristic values afterwards in the evaluation. And same here as a standard maneuver on low friction, that means in ice and snow when you drive on winter test, braking on snow, acceleration on snow and ice, or braking on splits. That means on one side of the road is ice and on the other side is asphalt, so that you have different friction coefficients on the side of the car. Yes, and also power off reaction in circle or driving straight. So there's a big bunch of maneuvers also when you drive on the winter tests. The next group here, the extreme maneuvers, are here slowly increasing steer, slalom test, double line change test, and the group of NHTSA maneuvers. And these extreme tests have normally not the normal weight on the car, but their cars are fully loaded, almost or nearly fully loaded, and you make the tests in direction of the results of the steering, that the steering is okay, and that that the rollover stability is okay, not the steering, sorry. We will have a look afterwards at the end when we have a special look to the sine versus dwell test. Next group is steering maneuvers. Here's a steering returnability or steering release, oscillation. There's a special weave test also in the International Standard Organization group, parking test, steering effort, and so on. And the last one here is a special maneuver test. Here's one example, is a car trailer stability. It's also in the International Standard Organization norm. So that's an overview about most common and valid and important maneuvers. And now I want to continue with a question: what do we need to measure and why? And for this, I have here the closed loop control system, driver, vehicle, and environment. Here in the center, you have the vehicle. That's in the system theory, that's our system. And in the vehicle, there's a driver. He is the controller of the system because he sits in the car and he is steering, braking, and so on, what he can do. And the driver, normally he has a task, that's the input for the controller. Maybe the street will follow a curve, and so the driver had also to follow the curve. Yeah, so then, in this example, the driver will steer, give an input to the vehicle system, and the vehicle will have a reaction. That's the control value. And then the reaction of the car is normally not exactly this what the driver is expected, so I need to correct. And you see here, then you have a loop, and that's the loop of the control system. And here on this side, you have also some errors, road disturbances, maybe lateral wind or from the road. So that's an additional input here in the system, what has the driver to correct. So when we make vehicle dynamic analysis, we want to make determination of the transfer function. We want to know what's here inside in the system. We want to describe the system. So we must have a look to these signals, what's going here inside to the system, and we must have a look to this, what's going out of the system. And when we measure with our data measurement technique, what's going in and what's going out, then we can make here the analysis of the system of the vehicle. Yeah, and then what's the question? What's going inside to the vehicle? That's, you see it here. What are the errors, the road disturbances? And here the other input is the driver. And the driver, what can he do? He can steer with his hands. So we had to measure the steering wheel angle and also the torque, with which power or force he needs to steer. And he can use his feet to press a driving pedal, and the result is speed of the car. So we also had to measure the speed. And when we measure the speed in longitudinal and also in lateral direction, then we measure all here of the input. And the other thing is, here the errors. We had to measure the errors, or we had to guarantee that the road disturbances or the environment has no influence. So that means measure in wet condition, measure with low windy, measure with real flat surface on asphalt. And when you guarantee this, very good road, then you have nearly no errors. And that's also the only thing you need to measure is steering wheel angle, steering torque, and the speed and side slip, resulting side slip angle here on the inside. And the outside here of the system, so this is the movement directions of the car, all the movement that are the accelerations, the angle rates, and the angles in all three dimensions. That's the reaction of the car, and you had to measure this, and then you have everything you need for the analysis afterwards. Here are the directions of movements. The three translatory movements, the longitudinal, lateral, and vertical are important. The rotatory movements, roll, pitch, and yaw, the rotation. And these movements are also all defined and normalized in the international standards. And I want to mention here that there exist two coordinate systems. We have the body coordinate system of the vehicle and also the inertial coordinate system. That's the coordinate system of the Earth. And when you put a normal acceleration sensor in the car, you have also always a problem when the car is moving. Yes, you have a roll angle maybe. Then you measure in the body coordinate system. And then because of the gravity of the Earth, we will also have an error on the sensor, on the acceleration sensor. And that's the reason why in the car industry it's very famous to measure with so-called inertial measurement systems, who are able to measure here in the inertial coordinate system. Here is a very short or small picture to give you an impression about the basic measurement technique. What's the minimum you need? And when you think about the presentation slides 1 or 2 before, yeah, you see here the measuring steering wheel is needed, and also here speed sensor. And here for the output, the strap-down platform, it's an inertial measurement system. And when you measure this here via CAN bus and USB cable to a notebook with a software, data acquisition software, then you have everything you need for data acquisition or for the analysis afterwards in driving dynamics. In this example here, I have a notebook, and I mentioned here the Moses software. You see here a screenshot, and this is the software we use very often or normally for data acquisition in driving dynamics. And afterwards, I will show you also some screenshots from this software to explain the results and what you see after the measurements directly when the measurement was finished, to help the driver to control the measurement if everything was okay while he did this maneuver. So now let's begin with the first maneuver, the steady state circular test procedure. How it's driving. Driving, you drive the car here in a circular, and so in the standard organization, there's mentioned a radius of about 40 meters, or you can do it with 100 meters driving. And here you see the measurement signals, the speed, driving speed. You begin with very low, and then you increase the speed more and more and more and more. That's one possibility of doing the maneuver. The other one is to drive with one speed and make one round and then stop the measurement, increase the speed, and drive always constant while doing one measurement. Then you will have steps of speed and have a lot of measurements, and you can afterwards make the same evaluation. And when you drive like this here, increase the speed, then it's very important that you don't drive accelerate too fast, because at steady state circular test, that means that you drive here with a very low increasing of speed. That means that you have 1, 2, 3, 4, not only 1, 3 or 4 minutes for each test run. Here at the beginning, when you drive with 40 meter, you have a so-called Ackermann angle. That's the initial steering wheel angle. And then afterwards, when you increase the lateral acceleration, you see here, increasing, increasing, increasing. Then you need to steer more and more. And that's because of the understeering of the car. Here you see the roller angle increasing more and more, and here the side slip angle from the Korowitz sensor. When you plot this above the lateral acceleration, then you can calculate here some gradients. From the steering, you can calculate the self-steering gradient. That's a gradient here. Then you can calculate the roll angle gradient, and you can calculate the side slip angle gradient. And these gradients here are important characteristic values to describe the behavior of the car. Here you see the screenshot I mentioned before from the Moses software when you do a measurement. And here you see we have 4 test runs. And the last one here, that was a measurement with the number 4. And you see always here in the special color was the last measurement. And you see here the first, third, second, third, and so on, all of your measurements. And you see an evaluation to give the driver the information if the measurement was okay. And here in the x-axis, you see the lateral acceleration. So that are nearly the diagrams you will calculate afterwards in the evaluation in your office. And here directly after the measurement, the driver can have a look to the results in advance. So that's not absolutely accurate, but it gives him an impression also about the how good he can reproduce each measurement. How good can he repeat the measurement? And when one curve laying over the other, then the driver gets the feedback, yes, he can good repeat this measurement, and that gives him the confidence that everything was okay. Here, when you press page down on the software of the Moses software, you get another site with some additional charts. Here you see the torques, steering torque, and here the speed, yaw angle, and yaw rate. Data evaluation. I will have here some examples from measurement in Buxberg. That's a German proving ground. That was some years ago. With this test car here, with the Skoda Octavia. And here you see is from the sky, from iBird perspective. Here's a measurement, the GPS dates when you drive the circle. And here when I zoom in, you see that the deviation here of the curve, the driver has driven that was less than 1 meter. So he was always very accurate on the circle. So here you see the time diagram from the steering wheel angles, blue curve here. And here's the speed, that was a black one. Increasing speed, constant radius. Here in this case, it was only a test measurement. And you had only 30 meters. Steering wheel angle, that was initial value here, 84 degrees up to 300 degrees. And the yaw rate here, starting with 0, continuing up to 30 degrees, and radial acceleration up to 8 meter per second square. So when we'll now have a look to the diagrams, with lateral acceleration here at the x-axis, when you make a classification or plot one channel over the other, then you see here the curve of the car with the steering wheel angle, the initial value here of 84 degrees, and then here the increasing and more and more and more, and you increase the lateral acceleration. That's on the one side, and here you see the curve on the other side. Also that means right turn and left turn. So the initial value was 84 degrees at 6 meter per second square. That has 120 degrees nearly, and that can be also a value for describing how much understeering has a car. You can calculate here a gradient from maybe 1 to 4 or to 5, and you can also put one value maybe at 6 or 7 or 8 to describe what is in the more higher region of lateral acceleration. What values do you have there? Here that's a steering gradient. And when you divide the steering gradient to the steering ratio, then you are independent from the steering ratio and calculate only the slip angle of the front axle. Then you have the self-steering gradient. And in our case, it's a value of 0.24. So when we go to interpretation here, you see the value of 0.24, then that's the question, is this a good value or not a good value? Yeah, that's always the question, are the values good or not good? And then that depends on a lot of things. It depends on what type of car do you have? Do you have an SUV, a sports car, or family car? And what kind of target in evaluation do you have? Do you want to build a very sportive car or not? And so this car here is, I think, in a normal region. A lot of cars are between 0.2 and 0.3 with this gradient. So that's here looks quite normal. And also here, when you have a look to the values of about 5, 6, 7, 8, then your steer here is low, increasing more and more. And that's also okay, because then the driver gets the feedback of the understeering increasing more and more. And yeah, when you drive this very high lateral acceleration, you will not have a surprise of the car that the car is doing something it did not expect. Here the steering torque, yeah, for the driver is always good, that he gets the feedback of increasing lateral acceleration here from the steering torques. That means when you have a higher lateral acceleration, the driver should feel a higher steering torque. So it's good for feeling the feedback of the driver when you see here an increasing of the steering torque, and in this case here, that's okay. And also the amount, when you have very low lateral accelerations, here you are in a region of 3 Newton meter, and afterwards here increasing to 5. That's in a very common and good range for the drivers. Yeah, and the increasing of the lateral, of the torque is until 7.7 meters per second square. That means nearly until the maximum lateral acceleration, the driver gets the feedback of an increasing steering torque, and that for him will feel very comfortable and okay. There are also typical characteristics for power steering. Here you see the side slip angle. There are 2 curves. This is here the side slip angle calculated to the rear axle. And to the rear axle you have with 0 lateral acceleration 0 degree. And this curve here is the side slip angle for the center of gravity. The center of gravity is between front and right axle, so you have here a little offset. But the gradients are the same, and you can calculate here the gradient, and side slip angle gives you always the information about the stability. And here you have a gradient of 0.25. Yes, and that's good stability, I think. It's okay. It's not the best, but it's okay. And when you want to know what's okay or what not, then we sometimes do some benchmark tests. That means we make also evaluations of competitor cars of other brands, and we'll have a look what are the values of these cars and compare it with the values of our cars. And the other thing is that you have also the possibility of driving and make your subjective judgment, and there are always some other experts driving and saying, oh, this car has a good stability, please make measurements of this car. And then when you calculate maybe in this car a gradient with much more lower, maybe 0.15, and then you get the feedback, yes, okay, 1.15 is feeling like this and 0.25 is feeling like this. And after years and years and a lot of experience, then you can make your plans for the next brands or for the next models you will you will develop, and then you can mark and say can make a definition of goals you want to have or you want to reach for your new model. So here the last was the roll angle. We have a gradient of 0.51, and that's also in a normal, comfortable, more comfortable area. And if the roll angle gradient is lower, maybe 0.4 or 0.3, then it's a very sportive car because the spring level is very low with lateral acceleration increasing. But 0.5, it's in the middle. Sometimes SUVs or so cars have 0.6, 0.7. Sometimes direction 0.8. So next maneuver, double lane change maneuver. Transient behavior and stability. The first one was steady state. That means a very constant maneuver. And here we have the opposite thing. We have a very transient, very dynamic maneuver. And we will have a look to this. Here you see the animation of the car driving through, here's the 3 areas of cones. The distance here is 125 meters. Here you see some photos are turning from one area to the next area and so on. And in this maneuver, you have some different tasks. You can do a lot of interesting things. The first thing what also the journalists are doing is to test what is the maximum driving speed you can reach with a car. So you make a speed measurement, and in the National Standard Organization norms, there was a definition that you count here where you see the green bar and here in this point. And then when you measure the time, and then you have here the distance, then you can calculate the mean speed, the mean velocity. And you can also make a questionnaire for the subjective evaluation. And afterwards you can compare this, you make a statistic. And the higher the speed is, then the car is much more sportive. And in the tests of the journalists, you will get more points. Here you see the time signals for a steering wheel angle. It's typical here, lateral acceleration, roll angle, and here the driving speed. And here, when you make a measurement, then you can make a position on the green bars here and make a position of a light bar. And then you get here a pulse when you are entry in the first area, and here in the middle of the third area, you get also a reflection impulse from a light bar. And then you can calculate here the mean speed, and you exactly know that here that was the beginning of the first area. So driving as fast as possible means that no cones are allowed to fall. So you had to train a lot, and when the cone is fallen, then that measurement does not count. And I'm sure when you compare tires or compare cars, you can evaluate their ranking only with the speed. The other thing is you can drive a little bit lower, maybe only 100 kilometers, and make here such measurements. And when the same driver, because each driver has his own driving characteristics to pass here, when the same driver is doing the measurement with the same speed on another car, then he feels the difference, and you can also see difference, maybe here also in side slip angle or in roll angle, or and you can calculate differences and can make evaluation in such direction. Here you see the view from the iBird. Here's the first area, the second area, and the third area. And here also a screenshot from the Moses software after here 6 measurements. And you see here the speed is always increasing more and more. So the shift together here, the time signals are shifting together more and more and more. Here you see the signal from the light bars. Here you see the speed increasing more and more and more. And last measurement was 100. And for this car, I think it's also not the limit. You can also increase and can test what is the maximum speed that's possible. Now, here was 100 km/h, the last measurement, steering wheel angle up to 70, yaw rate 20 degrees per second, lateral acceleration up to 8 meter per second square, and no pylons were fallen. That's always the important thing. And yeah, like I said, higher velocities were possible. The slalom maneuver is similar. Yeah, 10 curves, 180 meters. Same speed measurements here, the first and the last cone there. You can put a light bar when you make measurements, or you have other technique to start and stop the time measurement and calculate the mean value of the speed. And you can also make a questionnaire for subjective evaluation and speed measurements and compare them, make statistic evaluations. And also here you can measure the objective channels, the measurement channels, and make objective evaluation. Here's a offline screen of the Moses software from the slalom test. Here one measurement. Here's the steering angle, the lateral acceleration, yaw rate. Yeah, but this maneuver, it's always hard to compare measurements because each driver has his own strategy. There is no forced input signal for the driving. Yeah. So there is a big deviation between the driver A, B, C, and so on, and that makes it very hard to make a standard evaluation process. One thing is the first method only to calculate the maximum speed. If that works, that's fine, and also to get some subjective impressions and feedbacks, but much more evaluation is very hard. And the next group here is extreme tests. And the extreme tests are sometimes the same maneuvers like a standard test, but yeah, these are criteria of active safety. So that means the stability of the car and also the maximum loading condition is important. Here are some words to the history. That means in 1998, international companies in all types of the world, they have looked to this theme, to the rolling dynamics. That means the rollover stability. And they, maybe you heard about the Moose test, where the Mercedes car was fully loaded and then had a special double lane change maneuver, but not with this we looked before. It was a little bit shorter, the distance between the areas, so the speed is not so high. The German lane change maneuver or extreme sinusoidal steering input or slalom test, you can also do here extreme test with maximum load, and then with another focus not to beat the highest speed, but to have a look to the rollover stability of the car. And also here the steady state cornering with increasing steer angle and with roof rack also. So that all was activity started here more than 20 years ago. And yeah, that was always developing and developing. And here in the 22 to 28, when the ESC systems came to the market, electronic stability control systems, some more maneuvers were defined because now the ESC system has the ability to avoid the rollover. But the other thing is when they brake a lot, then maybe the car is only driving straight and cannot curve. So the NHTSA, that means National Highway Traffic Safety Administration, started to make definitions and thinking about a lot of maneuvers to describe this conflict. Yes, and maybe you remember in the press nearly 15 years ago, we had in the press such photos. And they created the consumer union test, the fishhook test, J-turn test, slowly increasing steer, and also the Sine with dwell test. And that all were tests to describe that the car is safe, that the ESC system is working, that no rollover will occur, but that also the movement to the direction right or left is also good enough that you can pass the obstacle in front of you, that you will not have an accident when something is before you and you want to curve around this. So here's our extreme maneuvers. We also have the braking in a turn with high speed, is also extreme maneuver, or pulse steering input. And here you see steering robot required. So some of these maneuvers are extreme and need a very specific steering input that is only done with a steering robot. Also here's a NHTSA fishhook maneuver, and at least here's a NHTSA Sine with dwell maneuver. So, and that's always important. Most loading condition is maximum payload. Here's a photo of a steering robot from ABD. We are also using here this model called Torus robot, because here you have the advantage that the airbag system is always working, because here it's empty in the middle. That's a great advantage for the safety of the driver. Finally, here we will have a look to the Sine with dwell test. Basis is this for the NHTSA or MV SSS 126 regulation. Test execution of the Sine with dwell test. That's a little bit complicated because you need a preliminary test before, because you had to determine the required steering amplitude before the NHTSA maneuver Sine with dwell with a preliminary test, and that's an increasing steer. And the reason is that this maneuver, the steering angle depends on the characteristic behavior of each car. Each car is different and has its own special angle depending on the steering ratio and the other vehicle dynamic characteristics. And so you need to make a test before to get the starting angle for the tests. We will have a look. And in one variant, then increase the steering amplitude. And for this test, the initial value is this angle at a lateral acceleration of 2.94 meter per second square in the increasing steer maneuver. We will have a look. And then increase this value by the factor 0.5 till the factor 6.5, or steering amplitude is 270 degrees. And carry out the maneuver in both directions. So here I have a screenshot of the primary test maneuver, the increasing steer. So that means you had to drive here with 80 km/h. And then here you see the steering angle, increase the steering angle more and more and more. And then you calculate here at the point of 2.94 meter per second square, what angle do you have in this point of measurement here. That is 2.94. It's marked here nearly at above 4 seconds. And then you calculate what angle is needed for this lateral acceleration. And here you see the evaluation for each test here in the data sheet of the Motors software. And you see here that's around 79 degrees. No, that was the speed, sorry, 29 or 30 degrees. And here at the end, here is a mean value, that means 29.9. So that's the starting angle here for the sine with dwell test. And sine with dwell, that means you steer a sine, and here you have a dwell time. And the dwell time, that means the steering angle is constant for half a second, and then the sine is continuing. And the amplitude is starting here with this angle of the measurement before. That means 29.9, let's say 30 degrees in this case. And then you make a variation of the amplitude. You start with 30 and then 1.5. That means 45 degrees, then 60 degrees, factor 2, 75, and so on and so on and so on. Make always at 80 km/h. And yeah, hold the steering wheel angle here for 500 milliseconds. That's the dwell time. And the steering frequency is 0.7 Hertz. And then you make measurement in one direction and also here in the other direction. And afterwards, here when you have left look of all the maneuvers you do, you have this. That was here's the first measurement, then maybe the second, and so on until 270 or the 6.5 factor. And then you make the measurement in the other direction. Here you have a video, one direction, hold, and then the other direction. Now look, one direction, other direction, hold, and now back to 0. Again, one direction, other direction, hold, and 0. Then in the sine with dwell description, there's also very good description about the evaluation afterwards. And in the Motors software, we can also make evaluation directly after the measurement. And here you see, like before in the screenshots, here that's the 5th or 6th measurement, and you see increasing more and more and more the steering angle. And here that's the lateral displacement must be calculated. And there is a minimum lateral acceleration displacement of about here 2 meters that must be reached. So that means the ESP system can work, but it's needed that you have a minimum lateral displacement of 2 meters. And you see here each measurement calculated, this is this. So you can imagine when you continue making here the measurements that this car will have no problem here because this curve is running here in this direction. And also is a calculation of the yaw rate, because 1 second or 1.75 seconds after the steering, there should be only a very few yaw rate remaining. Should be here in these limits. And you see this car here is very stable because there is no additional yaw rate. So that's an advantage, big advantage here of the software, that you can have directly look to the results. And here there's also a column TWL, that means two-wheel lift. And it's also calculated if the car here has a two-wheel lift. Here's always no. And here, that's the criteria of the two-wheel lift. We have two distance sensors to the ground. And then the data acquisition software, you can calculate them to a distance signal. And there's also a criteria for the two-wheel lift. And yeah, here you see that you have no problems. Here's the other. The roll angle is only here around, if you have an offset of -2, so 7, that means around 5 degrees, and it's not increasing in this case, and then we have no problems. That's it for the end of today. Thanks a lot for your attention and for joining my presentation. I hope there were some interesting topics for you.